happen with all the CO2, and this is actually for real. This is something I used to study. It was space elevators as a way of leaving the Earth rather than conventional chemical rockets. And so the space elevator molecule of choice or material of choice is the carbon nanotube because of its strength to weight ratio.
Sure.
So what I want to see, and I've talked about this a little bit before, and it does get right down into the nitty gritty and the possible future of bioenergy and carbon sequestration. But if you've got your CO2 sitting here, CO2 molecules, hanging out in the air, bring that in through a bioreactor. So right now, what a typical bioreactor, you think of like algae or whatever. It's taking that gaseous form of CO2 and converting it into liquid or solid or gelatinous or whatever you want to consider algae to be. But what I want somebody to do, and if I'm ever directing the National Science Foundation, I'll put an RFP out for it, is invent some kind of enzyme that takes the CO2 in, and what comes out, well, what we all love, oxygen and carbon nanotubes. So, and it's not that far-fetched. I mean, our own DNA replication, and these are just little, carbon nanotubes is more or less graphene. So somebody needs to invent a graphene enzyme.
Something that's going to put the carbon in that shape.
Yeah, exactly. And now you've got your space elevator. So now all of your nasty CO2 in the atmosphere is now literally. Then you fire a rocket, put that bad boy in space. And I don't know if you've seen these before or not, but here's your space elevator, and you've just got a little rope that heads down, and you have to have a counterbalance, and then your robots can just sort of climb up and down and get to geosync orbit and just drift off. Yeah. So there you go. There's my bioenergy fantasy for the future.
I recently saw that one of the first commercially viable graphene-based batteries was hit the market.
Oh, really?
And it's a company that's focusing on drones.
Okay. So the graphene is a light battery substrate. Nice. Yeah.
I'd say the efficiencies on it right now aren't necessarily a screaming amount higher than what we're seeing off these mobile batteries, but
They're competitive.
they're predicting it's going to get better. And
Cool.
they're light.
Cool. All right, so here we go. Back to Earth. So the heat rate says, while efficiency is reported as percent or fraction, heat rates are typically reported in the thousands. So, for example, average coal heat rate is 10,300 BTUs per kilowatt hour. So here again, you got to be careful. You're keeping track of units. He just snuck that BTUs per hour into the denominator. So it's energy divided by energy. So there it is in the 10,000s. Natural gas steam engine, a little bit better. It's in the 8,000. And I think another thing to keep in mind is that the units are a little bit wonky. 1 BTU does not equal 1 kilowatt hour, obviously, and that's where those thousands come into play.
Gotcha.
Okay. All right. Material balance. I think we did a pretty good job of this last week. We did 2.1. We did a little bit of stoichiometry. I drew out a picture. I don't think we need to hit this again too hard because I think we covered it pretty well last week.
Homework this week gets into it.
Good. Energy balances, I think we did this pretty well last time too. Okay, let's look at this. We didn't really hit enthalpy to much degree last time. Okay. Heat energy is represented by this term. So it's the sum of the masses times the sum of the enthalpies. So let me write that out. Okay, so the way the book, or the notes have it written, sum of mass sub I, h sub I, equals what? Well, obviously, and I'll do a little dimensional analysis here, units analysis. The units of little m for mass are just mass, big M. The units or dimensions for enthalpy is, well, it's just energy per unit mass. So in this case, we would measure this in kilograms, and we would measure this in joules per kilogram. So obviously, multiplying the two together, you're going to get your total enthalpy, your total heat. Now, another thing to keep in mind is that little h is an intensive variable, and big H is extensive. What does that mean? Well, it just means just really what it says, that little h is how many joules you have per kilogram. So, and good example, here's my coffee cup. There might be, shoot, I don't know, let's just say a half a liter in here. It's at some temperature. I can put heat into it, in the microwave or on the stove top. I didn't get any more mass, as long as steam wasn't coming up, but now I've got more heat and I've got more total enthalpy. So little h is intensive. It's how much heat there is per unit mass. Big H is extensive. How much heat is there? Or, thermal energy. Okay. Kinetic energy, we've seen before. Potential energy, he left off the M there, but I think we went through this diagram in a lot of, the only thing we didn't cover very much is the enthalpy last time, so the other two are pretty clear. Oh, and then, so another way to write that is just mass 1, enthalpy 1, plus mass 2, enthalpy 2, plus mass 3, enthalpy 3 equals. And so, we all have, did you not get your coffee there, Jason? What happened?
No, it's returning.
Oh, okay. But, if we all three had our coffee cups, mine could be M1H1, Jason's M2H2, and Damien's H3H3, and we just sort of add up, and that's our total. Yeah, so that's how to just go from this summation notation into an equation. You add them up, and that's your total enthalpy. All right. That's good. All right. Now, earlier in the lecture, I said that typically when you're looking to see what's driving a chemical reaction, it's some portion is going to be driving it towards greater entropy, some portion is going to be driving it towards chemical equilibrium, where nothing else is going to react. We just mentioned that it's incredibly complex. The concepts introduced are important. We won't dwell on them much. Here are what we are going to dwell on. Thermodynamic relations that can be used to determine how and to what extent it will proceed. Usually this is looking at the what's called the Gibbs free energy. Willard Gibbs, if I'm not mistaken, was awarded the first PhD in engineering in the United States of America in 1906 from Yale University. I think there have been other PhDs awarded in other parts of the world, but if I'm not mistaken, he was one of the first to get a doctorate in this field. And he basically said, okay, all of these chemicals reacting they're exchanging molecules, atoms back and forth, but they're also exchanging energy. And if what's called the Gibbs free energy is greater at the end, more likely than not, that chemical reaction will take place. And we can get into that in a little more detail later. Most chemical reactions do not proceed to ultimate completion And, there's a few reasons for that. I mean, we can even go back to our car engine. You're not always going to get just perfect. I mean, in a perfect world, what's going to come out of here? Well, just CO2 plus H2O. There's nothing else over here. There's carbon, there's oxygen, and there's hydrogen. And these are the simplest two molecules you can expect. Well, of course, some sulfur snuck in, some phosphorus snuck in. If you got the thing too hot, some nitrogen came in too. But there's a lot going on. I mean, there are trillions of molecules bouncing around, and it's sort of like, date night. Somebody's going to go home unhappy. Sorry, it's just yeah. So.
When you're doing the stoichiometry of it, you're doing the balance, and you have leftovers. Is that kind of the stuff that comes off, like your reaction doesn't go to completion, then it ditches?
Yeah, right. And so everything we're doing right now, up to now, is just theory. So the question is, what are the leftovers? Hopefully, later this semester, we'll actually get some experience with that. We're actually buying a Testo 350 5-gas analyzer. So it's going to measure NOx, SOx, everything coming out. And we'll be able to say, how accurate are our predictions? How complete is our combustion? So, yeah, I mean, what goes in has to come out. It's just the question is, who's dating who on the other side? Yeah. Okay, there we go. Gibbs free energy function is useful for calculating the extent that reactions proceed to completion. So we'll hit that a little bit more too. All right, these are some really good notes. Brian's done a good job putting these together. Let's take a look at the example problem. Okay, we'll make this a little bit bigger. There's our word, stoichiometry. How they combine different proportions, combustion, usually oxygen, we know that. CO2 and water, we just discussed that. There's our conservation of mass, what goes in has to come out. Methane is the fuel, I think we covered that already. Yeah, okay, so propane is C3, methane is C1, ethane is C2, there's propane, it's C3. We're going to add them together. You can see, obviously, there are 3 carbons on this side, but not on this side. So first thing to do, well, let's just stick a 3 right there. Well, shoot, now you've got 6 oxygens over here. You had another one. If we stick a 5 on that, now we have 10 oxygens on the left-hand side, and the only thing left to do are the hydrogens. And in this case, it actually works out pretty well. If you just stick a 4 on that guy, since you don't have to do any balancing here, it just works out. Now, if you had other chemical species going in, it's going to be more complicated, but in this case, there are some formulas for figuring out this exactly, but in this case, with 2 reactants and 2 products, a little bit of trial and error you're going to get there, and most of it's integers. Yeah, and this is also important. So a lot of times, when people talk about carbon pollution, so the question is, how many tons of carbon are going into the atmosphere versus how many tons of CO2. And let's just see if he's got, let's see what he's got down here. Yeah. Right, okay, so let's just go through this guy really quick. So in this case, carbon well, it's the 12th element. It has a molecular, it's the 6th element, has a molecular weight of 12. We covered what pound moles were last time. So 12 pounds of carbon is the same as that many pound moles of carbon. Hydrogen has a molecular weight of 1, and so it's 1. So we're basically just taking these coefficients. There's your 3, there's your 8, and in this case, all we're doing, we've got 3 times 12, that's 36. 36 plus 8 is 44. So 44 pounds of propane per pound mole. So that's our first.
This is how we put together the correct quantities to see our reaction go to completion, right?
Yes, yeah. So the moles are keeping track of the actual numbers of atoms or molecules, but they're doing it they're doing it 1 mole at a time, or even 1 pound mole at a time. So you're counting 2.26 or sorry 6. What is Avogadro's number? 6 times 10 to the 23rd. Yeah, let's just go dig that guy up really quick. So you're actually keeping track of that many molecules or atoms at a time because you can't see the thing. So, so these are the 2 reactants. Those are the 2 things on the left-hand side of the equation. I think I can even get that up here. And then on the right-hand side, we've got CO2. So again, we've got 1 carbon. It's 12 pounds per pound mole. Oxygen is element 16. We've got a pair of them, so 2 times 16. 44 pounds of CO2 per pound mole, and then same thing for the hydrogen coming out. And nitrogen is just coming along for the ride. For every N2, nitrogen is element number 14 times 2, 28 pound moles of nitrogen going through 2. Okay, so for a given combustion process, if you've got 10 pounds of propane in your propane tank and you're going to go burn through it, so 10 pounds, and if we head back up here, we can see that there are 44 pounds of methane per pound mole. So we know that just running that through, and let's just do the calculation here to convince ourselves. 10 divided by 44 equals 0.227. So that's that really is the number of propane molecules in pound moles going out the other side. And so that many pound moles has to interact with that many pound moles of oxygen. So again, sending that through, 0.227 pound moles of propane. Let's see where we're getting our 5-to-1 ratio. 5 pound moles of oxygen per 1 pound mole of propane. Where is that coming from? Well, it's coming right here. Because there's 5 oxygens and there's 1 propane. You gotta shove 5 oxygen molecules for every one. So that's what that 5-to-1 ratio is right there. So it tells you you're going to burn through this many pound moles of oxygen in this particular reaction. So to review, we converted pounds of propane to pound moles of propane. We then got the ratio, the combustion ratio of propane to oxygen, and said there's this many pound moles of oxygen. Do the same exact thing for CO2. Start off with the same number, 2.27 pound moles of propane. Where's this 3-to-1 ratio coming from? In CO2 and propane, right here. 3 CO2s per every propane. So, I mean, so we're actually working at the molecular level and at the complete mixture level at the same time.
I like that about that molar weight.
Yeah.
I mean, it took me a minute to figure out what it was.
Yeah, and these 1.1, this 0.6, it's much easier. You're not writing you're not digging like, what the heck is Avogadro's number? it's a bushel or whatever. You know? And then then you're just dealing with these nice little fractions. So this many pound moles of CO2. Do the same thing for water. Where does this 4 and where does this 1 come from? Well, right up from this nice little bit of algebra we did earlier. Okay, and then to find the actual weights, we've got the number of pound moles of oxygen, and there are 32 pounds of oxygen per pound mole. Why is that? Well, it's because oxygen is a diatomic molecule. Oxygen itself has a molecular weight of 16, but it's diatomic, so 1.136 times your 32, there's your 36 pounds. So if you're going to completely burn 10 pounds of propane, you better have 36 pounds of oxygen laying around. And if it's going to burn completely, you're going to make 30 pounds of CO2, and you're going to make 16 pounds of H2O.
So, depending on where you're burning this at, obviously, if you're burning it in Beijing where the air is way different than to here, it's going to totally affect.
Yeah, that's your question. That's a perfect question, and it leads to this too. So let's say you are somewhere where there's only 19% oxygen and 75% nitrogen and 2% crap. You're going to need to basically. So if you have a 2% difference in your oxygen, you're going to need to pump through 2% more total volume of air through the process. Yeah. What he's done here is just taken those 21 and 79% and just looked at the ratio. So if you know for every 5 moles of oxygen that goes through, this is answering your question hopefully, if you're in a 0.79 to 0.21 ratio, this is how many moles of nitrogen will go through. If that number was different, if that was 79, if that was 21, it would be larger. You would have, and of course, because you'd have to pump more air through, and thus, therefore, more nitrogen is going to go through, right there. So this stuff is just kind of coming along for the ride, as long as you're low temp. All right, well, hopefully that's a good little chunk to get you going on this week. Yeah, Brian's done a really nice job with this course.
Yeah, it just flows really well.
Yeah. So there's your homework, and you're off to the races. I'll do some grading on Sunday. If not everyone's gotten to the, I'll at least grade the first 2 weeks by Sunday, so you're feeling good about that. And then just be sure you've got the week 3 homework and the week 3 quiz done before I see you a week from today. So that's all I ask. That's all I ask. Okay. All right, guys. Thanks.